Okay. Today we will keep talking about software security, especially relative software security. Last week we talked about the background knowledge you need to understand the next several sessions. First, we will talk about stack-based buffer overflow. We will understand how stack works on Linux 64-bit version and also 32-bit version. And the objective is to identify buffer overflow in a program, especially at the C library, C program level, and also to exploit buffer overflow vulnerabilities. So today we will talk about some simple bugs. Next week, Wednesday, we will talk about more complicated bugs. Then after that, we will move to heap-based vulnerability and also ROP. So that's the only three topics we will cover in the software session. Then we move to network security. So a little bit history about buffer overflow. So back in 1996, there was a publication on the FLAC, PHRACK. That was an online blog, online journal. The journal still exists, but it's not that important anymore. But back in the 90s, a lot of hackers they published articles on how to hacking things there. So back in 1996, there was a publication titled "Smashing the Stack for Fun and Profit." So this is probably the first well-documented approach on how to exploit buffer overflow. Even though the buffer overflow exists before that, but most people didn't know how it works until this article. And back in the 80s, there was a graduate student, Robert Morris. He was from Cornell, not very far away from us. So Robert Morris, he is a professor at MIT. So back in 1998, he developed the infamous Morris worm, and it is believed it was the first computer virus of that kind. This was actually maybe the first convicted computer crime in history, and Morris worm used several buffer overflow vulnerabilities and attack services on other computers. So back then, the internet was still small, and Morris worm took down maybe 10% of the internet at that time, or maybe more. I don't remember, but that was the first time this buffer overflow got really attention. So, but even still today, or several years earlier, back in 2019, you can say that. So MITRE is a big company, DoD contractor. So they were announced the top 5 most serious vulnerability categories every year. And back in 2019, you can say that buffer overflow was still one of the most important vulnerabilities. Kind of the first one is related to buffer overflow, improper restriction of operations within a memory buffer, and there are several others, auto-bound read. Those are also related to buffer overflow. You can see others, so cross-site scripting, that's related to web, which we do not really cover in this class. There is also secure injection, use after free. We will cover this one a little bit a week from now. So we'll first talk about a stack-based buffer overflow. So the goal is to overflow some buffer on the stack. So we need to understand what does the stack look like. We need to understand how a function really works in our computer system. So what do we really store in a function? Of course, I mean, first of all, there will be code. Those are eventually compiled into CPU instructions. Then there will be parameters. Those parameters will be provided to those functions. And the function, if you program at a C level, usually have one return value, but you can have multiple return values actually. If you pass some of the return values in the address as a parameter, you can have multiple return values. But the built-in return value is just only one. Programs, they have global variables, they have local variables. The variables are defined inside a function, they are local variables. There are temp variables. And also, at a C level, you do not really know is there are also return addresses. If you call a function, eventually that function will return back to whoever calls that function. To achieve that, there will be function frame pointers and the previous functions frame pointers. And those will need hardware support to implement. So let's start with some simple things. So firstly is global and the local variables. Global variables in C are defined outside of a function or any function. And the global variables hold their value throughout the lifetime of the program. And they can be accessed inside any function or outside of any function. Well, I say, everything will be in the main function anyway. So they can be accessed by any function, basically. So they are stored usually in the .bss section or .data section for global variables. Then for local variables, they are declared inside a function or inside blocks, and they can only be used by statements that are inside that function or block. And local variables are not known to functions outside their own function. So here is a simple example with both global and local variables. Right-hand side, we have the main function. The main function has two local variables. One is li. I name it L, means local. I means integer. This one is initialized integer, and another one is uninitialized. So one of them has a value 10, another one, when you run the program, when you first enter this program, its value, its content is not defined. It could be some garbage value. Technically, there are other local variables, like those parameters. The parameters are stored at the same place as the local variables, also on stack. Then we have 4 function calls to a C library function printf. Then another function called function temp. We have 2 global variables, gi and which is a string in this case, and we also have another global variable which is a pointer. Then this function func has a parameter p, 2 local variables as well. This function, this program, will just print out the address of all the global and local variables. In the main function, we print out the global variables address, both of them. Then you print out the local variables for main functions. So for this function, func, it print out its own local variables address and also the parameters address. Parameters, they are also on stack actually. So if you run this program, you will get something like this. If it's a 32-bit version, we put this program on our server, so you can feel free to run them. If we run them on a 32-bit machine, the result will look like something like this. So the global variable will add the address 56 something. This address could be changed, not necessarily always the same, because some security features. The local ones, however, you can say that will be a higher address. It's started with FF, because this is a 32-bit machine. The highest address you can go is just OF, right? Here we have 8 bytes. Then it will be the 4 bytes, sorry, 4 bytes, then the highest you can go is just 8 Fs here. You can see this is very near the top of the memory, and this is where excuse me, very top near where the this is where the stack is, and you can say both functions, local variables, they are at those addresses, very high address, and look very close. You can say, and they go down because the main function will call the func. So main function's stack will be created first at a higher address, then it goes down. So at the beginning it's D4, that's the main function's stack. Then it will go call the func, and it's that function stack will at a lower address at the main function, which will be A4. Okay, so A4 obviously is lower than D4 in this case. Then P, which is a parameter of that function func, its address is also on the stack somewhere. If you check the 64-bit version, similar results. Global variable will be at like 55. First of all, the address is much longer in this case. It's not really 64 bits on the system we're using. I think it's 39 or 40 bits. The stack will be at a 7F something. There should be some leading zero here, which I'm not showing. So what functions what information do we really need to call a function at runtime, and where are they stored? First of all, it has code. A function has code. The code itself is stored in the .txt section. The parameters will be stored on stack. They are like local variables. Some of the parameter will be stored in registers directly, especially for 64-bit. Last week, we saw that 64-bit has many, many more registers. And so registers are part of the CPU. Saving things there will be very fast. If you save things on the memory, it will be a little bit slower. Stack is part of the memory. Return value will be stored in a specific register. 32-bit, we just save them in EAX. 64-bit will be the 64-bit of RAX. Global variables will be in .bss, .data section in the memory. Local variables, either on stack or registers. Default will be on stack. Temp variables, the same thing. Temp variables, local variables are very similar. Return addresses, most of the systems will put the return address on the stack as well. Then the function frame pointers will use register EBP, RBP. Previous functions frame pointer will also be stored on stack. And those are the reasons why buffer overflow exists. So stack is just a scratch memory for functions. This structure is used in all kinds of architectures, from desktop, x86, servers, x84, to your smartphone, your smartwatch, the system, they all use stack. Usually, the stack, they starts at a higher memory address and goes down. Functions, they are free to save things onto the stack and use instructions like push or equivalent to push on other platforms, or pop from the stack to registers. So on x86 or 64, there is a register ESP, stack pointer, or RSP, 64-bit version. That register holds the address of the top of the stack, but the stack goes down. The top of the stack is a lower address compared to the bottom of the stack. For example, if we do an instruction push EAX. So this operation will decrement the stack pointer, which is ESP. In this case, it will first decrement the value of ESP. So ESP points to a lower address. Then it will store the value in EAX to wherever ESP points to. ESP points on the memory. So this one will save something in the register to the memory, to a specific location memory, which is stack. Pop is the opposite operation. When we do pop ESP, when we do pop EAX, we basically restore the value at a memory location pointed by ESP to the EAX register. So look at this instruction, pop EAX. In this instruction, look at the syntax. It doesn't really tell you where the stack is. It doesn't mention about ESP, right? But ESP is implied here. It will directly pop whatever ESP points to the register EAX. After that, it will increment the ESP. So to visualize this, I made several slides to visualize this. Let's say we have an instruction push EAX or push RAX. The only difference is the size of those two registers. One is 64. This one is 64 bits. This one is 32 bits. 4 bytes or 8 bytes. So let's say before we execute the instruction, the stack looks like this. The top is a higher address. The bottom is a lower address. So ESP points to some value X or RSP. And let me just use ESP, for example. ESP points to some value X here. Adjacent to X, there are Y and Z with higher address. Now we execute the instruction push EAX. Then we will just push whatever is value in the EAX to the memory. We will first decrement ESP. So ESP will move 4 bytes down. Then the value of EAX will go to the memory location ESP points to. So this is a push. Pop is the opposite. Let's say ESP points to the register points to the value X. We pop EAX, then whatever ESP points to will move to EAX. So EAX will equal to X. Then ESP will points to increment. So ESP will points to Y after this instruction. So the X here actually is still here. It's not changed. No instruction changes that. It's still here, but it's technically not in the stack anymore. Then one of the most important control flow instruction is the call instruction. Like when at the C level, you make a function call, and those function call eventually compared to a call instruction. If it's a call instruction to a offset to a memory location, that is called a direct call instruction. If that call instruction is called into a register, like the syntax here is call EAX. So when you decompile this program, when you say call EAX, you don't really know where it is calling to, because the value of EAX will only be determined at runtime. And if you say something like this is called an indirect call. So the call instruction does two things. It will first push the address of the next instruction to the stack. Then it will move the destination address to the program counter, or in x86, it's the EIP register. That's an instruction pointer register. Let's say before this instruction, the memory looks like this. On top, the green part is a stack. ESP points to value X. Then we have YZ on the stack as well. Then this is the code part. Okay. So the code we have before this call EAX was a push 1 instruction. So technically the value here 1x is 1. Then there is a call EAX instruction, then pop some instruction. Now EIP points to call EAX, which means the next instruction to be executed will be this call EAX instruction. Now we execute this instruction. After we execute this one, the EIP will point to next instruction. Usually, let's say if it's a push one, executed push, the EIP will move to it will point to the next instruction. But call instruction is different. It will not change the EIP sequentially by this. It will first push the address of the next instruction to the stack, which means the address of pop EBP. This address will be pushed onto stack. So after that, the stack will look like this. ZYX, the address of pop EBP. So after that, the destination, whatever is in EAX, will be moved to EIP. So EIP will not point to here. EIP will point to whatever EAX points to. And that is how we call a function. Return is the opposite operation of call. The return instruction on x86 is very simple. It's basically a pop. But this pop, you do not specify what is the target register to pop to. So the other pop instruction, you have a pop EAX, pop EBBX, then you know we are going to pop something in memory to EAX or EBBX. So return doesn't need that. For return, the target register is just EIP, the program, the instruction pointer. So the return instruction will pop whatever ESP points to EIP. And the EIP points to whatever to be executed next. So this tells the CPU to continue execute from another place. Let's say this is what the program looked like. There was a pop instruction before. Then we have a return instruction. After that, doesn't really matter. The stack looks like this, ZYX. So now we will execute the instruction return. So this instruction will pop whatever ESP points to the register EIP. So after this, EIP will be updated to the value X. And ESP will move up 4 bytes. So that is what return instruction do. We usually, at the beginning of the functions, we usually have those 3 instructions, push, EBP, move EBP, move ESP to EBP, then subtract ESP something. And those 3 instructions together, Intel introduced the 1 instruction to replace them. It's called the enter instruction. So sometimes you say, if you disassemble some code, you will say 1 enter instruction. Sometimes you say all 3 instructions there. That's usually happened at the beginning of the function. So that's called the prologue of the function. So those 3 instructions, let's take a look. What do they do? So before we enter those 3 instructions, the stack look like this. ZYX, ESP points to X. Now we will push EBP, which means the value of EBP will be stored on stack. That's why we have a EBP value on the stack. And at this point, ESP also points here. Then we are moving ESP to EBP. Then the register EBP's value is updated. ESP also still points to here. Then we just subtract some immediate number from ESP. Then EBP points to here. Then ESP will points to something lower address. So a lot of functions at the beginning will do this. what we're doing here is actually setting up the stack for the function, especially the subtract part is actually reserving room, space for those local variables. The leave instruction is the opposite of enter instruction. Let's skip this one for now. We will see more examples later so you can understand how this works. So functions, they will use a stack to allocate a space for their local variables, just like what we say here. This space is actually allocated for local variables. So the frame pointer, which is the EBP base pointer, it points to the start of the function's frame on the stack. Then each local variable, as you can see that in a function, the EBP will point to this place. It's a previous function's EBP. Then the local variables will be under that, right? So that's why each local variable, they will have different virtual address every time. However, they will have a fixed offset to the frame pointer. Let's look at one calling convention so you can see some detailed example. So when you call a function, there will be parameters, and those parameters must be passed to the function you call. And how do you pass some information? You either use the memory or the register. And the convention we use, like which parameter will be stored at which memory address or use which register to store that, is called the calling convention. The calling convention also defines who will push what value onto the stack or who will store those values. And there are many different conventions. They are different based on the processor you are using, the operating system, or just the compiler, different types of cores. We will mainly look at the standard Linux or C declare calling convention. In this convention, the caller, which is a function, will push arguments to the stack in the right to left order. Then it will execute the call instruction. After that, we will get into the call E function. Then the call E will push previous frame pointer onto the stack, which is EBP. This is the part we just looked at. It will also set up a new frame pointer. We'll move ESP to EBP. So now EBP points to its own stack frame. Then it will also create a space for its own local variables by subtracting some values from ESP. It will ensure that the stack is consistent on return. It will also return value in the EAX register. So this is this is a default calling convention when we compile C programs on Linux. We already looked at this part. There will be a prologue, those 3 instructions, and epilogue, also 3 instructions to restore the return address, also restore the previous EBP. Let's look at more concrete examples. Let's say, so here, this is the same program we just looked at, the one with global and local variable. And this is the func function, and this is a main function. As you can see that when we call in here, we say, where's the main function? We don't have the main function here. Let me go back to the main function to show you. So the main function here is very easy. we print out something that we call the function, func, with the argument, the concrete argument 10 here, right? So how it works at the instruction level is here. In the main function, it will first push A to the stack. So what is A here? We are pushing a number A. What is A? Yes, exactly. A is 10. So we are pushing 10 onto the stack. So we're putting the argument onto the stack. Then we make the function call using the call instruction. Okay. So after we make the function call using the call instruction, the control transfer to this function, which has these instructions will be like this. And in this instruction, you can say at the beginning we have push EBP, move ESP to EBP, then subtract 18 in hex, which is 24 bytes actually. Then we are moving this A to EBP minus C. This A so EBP minus C, that will be a local variable there. Then in this function, there will be several more function calls. So that we say at least 1, 2, 3 function calls. And they have the same function. Their function's address, right now it doesn't have the address, but you can say it will eventually be the same address. And that function will be, that corresponds to the 3 function calls to printf. Okay, that's the 3 function calls. So if we draw the stack, it will look like something like this. For any function, if you are using the standard convention, EBP will point to the saved EBP, and the addresses lower than that will be local variables. The address higher than that will be a return address and also the arguments for that function. So you can also change this EBP to RBP to make it 64-bit. Of course, the offset here will also change after you do that. Let's say several examples. Let's just guess what are those instructions doing. We have EBP minus 8. We are moving that one to register EAX. So what do you think at this address is EBP minus 8? It will be EBP points to the old EBP. The spaces lower than that will be the local variables, right? So EBP minus 8 and moving to EAX, basically we are just getting a local variables value from the memory to the register. Load the effective address EAX, EBP minus 24. This is basically we are getting a local variables address. If we are using positive indexing, EBP plus 8. So go back here. EBP is here. EBP plus 4 will be the return address. EBP plus 8 will be the first argument of this function. So this one is actually retrieving the first instruction, first argument from the stack to the register EAX. Then C is basically 12. C in hex is 12 in decimal. So this one is retrieving the second argument from the stack to the register. Okay, let's see a more concrete example. This is a very simple program, only 2 functions. One is main function, another is the fact, which is a factorial function. So this program will give an integer, a positive integer. This program will compute the factorial of that number you choose. And you probably implement something like this before. When you calculate the factorial, you can just use a recursive function to do this, right? So the main function will first check if there are two command line arguments. If not, it will print out how to use this fact integer. That's it. Then it will print out the string. The factorial of this number is blah blah, and the first one will be the first argument. The first argument is actually the second. Then it will call the function fact. The function fact will first print out I am in fact which number, then print out the address of this parameter. If that number is 1 or smaller than 1, it will just return 1. Otherwise, it will recursively call itself. It will call factor n minus 1 times n. Okay. So first of all, do you understand the recursive function here? Okay. If you understand the recursive function at the C level, then let's say how this is actually compiled. What was this eventually compiled to at the binary level? We go to our server. Factorial 32. So if we just run this program, when we run this program, it tells us you need to give an integer, right? So if we run this 3, the value is supposed to be 1 times 2 times 3, should be 6. It gives us the value. The factorial of 3 is 6. But what is more interesting here is how this is computed. Let me move this one here. So you can say the first time we call this fact function, what is the parameter we give it? What's the parameter we give to the first time we call it? It will be 3, right? So the first time we call it, we're actually calling factor 3. So that's why the n is 3 here. So it will print out in fact 3. Okay? Then it print out the local variable or the parameter's address. And in this case, the address is D680. After that, it will check this. Obviously, n is 3, so bigger than this. So we're going to run this instruction. And this instruction will call fact 3 minus 1, which is fact 2, times, it will call that first, right? It will call factor 2. Now we go back to the beginning again, but now n is 2. So that's why we print out in fact 2. Now we print out the address of this local variable n again. Even if it's the same local variable called n at a SQL level, but they are actually 2 different variables at 2 different locations. Now you can say n has a new address because this is the local variable for the second instance when you call that function. And it's at the D660. And obviously this address is lower than this address. That's why the stack grows into lower address. Then in fact 2, we eventually reach here, which we're going to call fact 1. So in fact 1, we print out in fact 1, the address of this is D640, right? Then for func 1, we are going to directly return to 1. After return to 1, we will go back to here. For function 2 is here. Then we go back to fact 3 is here. So from using this example, you can see that how a recursive function is actually implemented. Each function call has its own stack frame, and the stack goes from higher address to lower address. Let's look at another example. Also a very simple function. The main function will just call func. The func will take 5 parameters and simply add them together. In 32-bit version, those values, A, B, C, D, E, they will be passed onto the stack. So the main function will push them. The main function will push them to the stack. Then the func function will retrieve them again from the stack. For 64-bit version, they will directly use a register to do this. So let's go to 5 parameters, 32-bit version. We just disassemble this. We disassemble this program, then we go to the main function. You can see there are many other functions. Those functions, as a C developer, you didn't develop those functions. You only developed the main function, the func function, and those functions were implemented in the C library and compiled against your program. The main function here, you can say, we only need to look for the, let's go for entire syntax for consistency. So the main function here, let's say, where is the call to func? Here. The main function calls the func function. And to call that function, you also need to pass the parameters. And now in the C code, we have 5 parameters to pass. The convention is all of them will go to the stack. And the rightmost parameter go to the stack first. So translate that into assembly will be push 5, push 4, push 3, push 2, push 1. Then call func, right? So if you go back, if you go to here, you can say, that's exactly what happened. We're going to push those 5 parameters onto the stack, then call the func. After we call func, the CPU starts execute at the beginning of the func. So if func wants to retrieve those parameters, it has to retrieve from the stack, which will be EBP plus some value. So you can see that's, so this is the func function to retrieve the first argument. It actually retrieve from EBP plus 8 because EBP points to the old EBP. EBP plus 4 points to the return address. EBP plus 8 is actually where the first parameter is. Then plus C, 10, 14, 18 in hex. Those are for the other 4 parameters. Okay, so this is the 32-bit version. If we look at the 64-bit version, the same C code compared to 64-bit version. You can see here. In 64-bit version, the default passing convention is not to use the stack anymore. Directly, we move those values into registers, EDI, ESI, and 8D. We directly move them to registers. So this is directly inside of the CPU. Never leave the CPU to go to the memory, which will be much faster. Then the function part, you can say, actually, we have them here. Those one are EDI, ESI. The weird thing is, this piece of code is not very smart. Then it moves them back to the memory again, which is not necessary actually. Yeah. So now you can, those two examples, you say how parameters are passed in 32-bit and 64-bit version. Actually, even 32-bit version, you can use registers to directly pass parameters, but there are limited registers. So the fast call convention will use ECX to pass registers, but that can only pass one pass one parameter because there are not so many registers. 64-bit version, the first 6 arguments will just go to RDI. So the example I just showed you is use EDI. That's because the value is only 1. The higher 32-bit, we just use 0. So we were just using EDI. So the first 6 parameters will go to EDI, RDI, RSI, RDX, RCX, R8, and R8, those registers. If your function has many more parameters, those ones need to go to the stack because we don't have registers to use anymore. This part we actually also covered. Now, next, we are going to look at our first buffer overflow attack. This one, we are going to overflow a local variable. We're not going to overflow code pointers or the return address. The code we are using is called overflow local. This is the C code, and this is a disassembly of the vulnerable function. Here we have the main function. It takes 2 arguments. Then it will call vulfoo. Vulfoo is a vulnerable function. The first argument is hard-coded, just 0. The second argument is taken from your command line arguments. So whatever you input in command line eventually will be passed to vulfoo. So the vulfoo function looks like this. The first parameter is an integer I. Then there is a pointer P. There is a local variable J, which is initialized to the value I. In this case, the I is hard-coded, is always 0. So J, here, local variable, will be initialized to 0. After that, a local variable, a local buffer is defined. SQL level, we give it a name, buffer. At binary level, there is no name anymore, okay? Binary level, only instructions, no name. CPU doesn't need the name. At a SQL level, we define this buffer is 6 bytes. We know that in C code, in C, you are supposed to leave the last byte of a string as 0, right? Or C string when ended with a 0. So the buffer size is 6, but technically you can save 5 characters. The last one is supposed to be 0. Then we do a string copy from whatever you input from the command line to that buffer. This is where the problem is. So string copy, how it works is it will copy, no matter how long you give, to the target. It will only look for the ending 0. If it doesn't find the ending 0, it will keep copying. So you can copy 3 bytes if you input 3 bytes. You will also copy 20 bytes if you input 20 bytes. And the problem with that is your buffer is only 6 bytes. We will check the binary code later to say what exactly is at a C code level, it's 6 bytes. After compiler compile it, it may be bigger than that. But still, it will be something close to 6. So it's possible that the string copy will write over this array of characters. It will write into the local variable j. It will actually also possible to overwrite everything onto the stack higher than that. And there are a lot of important information there, like return address. After that string copy, the program will check the value of j. If the j is not 0, it will print out the flag for us. If the value of j is 0, it will print IPT the full. That's it. So if we run this program, overflow local, so it goes to overflow. Okay, those are heap overflow. Oh, there are overflow 1 and 2. I'm not sure which one. It should be 1, I guess. So let's look at the 32-bit version, overflow 1. If we just run this program, it will not do anything, right? Because the main function, if the argument is not, if you are not giving 2 command line arguments, the program doesn't do anything, just return, right? It doesn't tell you, hey, you need to give us 2. However, if you give 2 arguments, like say 5, 6, so this one is the first command line argument. This is a second program argument. So we gave a string, 5, 6. Whatever you put here is a string. It's not really a number. When we do this, the program will run, what? Program will copy 5, 6 to buffer. Then keep running, and j will be 0. That's why it will print out IPT the full. That's it, right? So if we give it a little bit more, 1, 2, 3, 4, 5, 6. 6 probably is also okay. But if we give 7, it actually gives us a flag. Okay? So this is the flag in the file system. This flag. Okay? Is in the content of the flag. But you cannot cat the flag. You cannot cat it because you don't have the permission to do so. However, this program has a bug. That's why this program itself is setuid program, which I explained last week. So when you input 7 here, what happens is that 1, 2, 3, 4, 5, 6, 7, that string will be copied to the local variable buffer. But the local variable buffer size is only 6 bytes. The last character 7 will be copied into j is 4 byte. It's an integer. Copied to the lower address, the least significant byte of j, making it not 0 anymore, right? So j will not be 0. So if j is not 0, we will call the function print flag. That's why how you get the flag. So the value you gave here obviously doesn't really matter. You don't have to give 7. You can give 8, 9, or you can get h, whatever, as long as it's not 0 anymore. Or you can even be more characters. But if you give even more characters, it will overwrite even beyond the j. It will overwrite the saved EBP. It may also overwrite the return address. So when you overwrite that, eventually what happens? Eventually you get a segmentation fault because your CPU will start executing at addresses that may not exist. Then it will generate a segmentation fault. But before that, it also print out the flag for you. But eventually generate a segmentation fault. Right. So let's spend a little bit more time on this one. First, let's look at the implementation of string copy. This string copy is a function which you'll never use anymore when you program. How it works is, this is one implementation of string copy. It takes 2 parameters. One is the destination, one is the source. It will simply copy the characters as long as they are not 0. copy them from the source to the destination. It doesn't care if the destination has enough space for that. Okay, so this is just the one implementation of this. Someone will prefer shorter implementations. You can just implement like this. Only 3 lines. You can implement this insecure function. Then, what happens in vol when we call string copy? Let's say we are going to say each instruction of this vulnerable function and try to understand how this attack works. Now we are at the beginning of vol. Imagine the next instruction we are going to execute is the first instruction of vol, which is push EBP. But this vol is called by the main function, which means the main function pushed 2 arguments to the stack and also put the return address on the stack, right? So at this point, the stack look like this. Of course, if we go up, there are many other things on the stack, but those are not important for us right now. Below this address, technically it's just garbage, nothing important. We have 2 parameters. One is the strings address, which is P. The other one is pushed to stack. Another one is 0. Okay, I. The other one is also pushed to stack. So the stack right now has an address for the string we just input and has an integer 0. After that, we have the return address, which is actually should be where is it? Should be the return address will be this right after the calling of vol, right? So now we are going to execute the very first instruction of vol, which is push EBP. So the value of EBP will be pushed onto the stack. We call that the old EBP. And because this is a push instruction, ESP will point to here. After that, we will move ESP to EBP. So we didn't change ESP in this case. We only move ESP to EBP. So both of them points to old EBP. Now we subtract 18 from ESP. Then ESP will move down from here to here. And the distance between this we know will be 18, which is 24 bytes, 18 in hex. After that, we are going to move EBP plus 8, whatever is at address EBP plus 8, to the register EAX. And we know that EBP plus 8 is the first parameter of this function, which is 0. Then EAX will be 0. After that, we move EAX to EBP minus C. Okay? So what is this doing? EBP plus 8 is the value I. At the beginning of the function, we have J assign I to J. So J is a local variable. So actually, this one we are initializing that local variable J. And that local variable's address is EBP minus C. And that is exactly where, in the middle of where we reserved this whole space, right? It's in the middle. So that is actually the local variable J. Of course, at binary code level, you do not say those names anymore. At binary level, the CPU doesn't care about program names. The CPU only say address registers. Then we subtract EBP again to get more space. Then we are going to make a function call here. This will be making a function call, and that's the string copy function call. The string copy has how many arguments? Exactly, right? So which means this is 32-bit. So we're going to push those 2 arguments onto the stack from right to left. So we're going to first push the source, then push the destination, right? So the first push here is push whatever is in EBP plus C. That is actually our source, right? That's where what we input at the command line. So we push that source onto the stack again. Then Then we will load the effective address EBP minus 12 to EAX. So this step, we are actually getting the local buffer's address, which is the buff we created at SQL level. And if you calculate this, you will notice that the buff is at address EBP minus 12, which is 12 is 18, right? 12 is 18. What? 18 in decimal. Then C and this local variable J is at C, which is 12 in decimal. So you know that, then you just subtract this one to this one. You can say the buffer is actually exactly 6 bytes. At a SQL level, you ask for 6 bytes. At the binary level, the compiler actually give you 6 bytes. Sometimes the compiler may give you more, but in this case, we can say it's exactly 6 bytes. Then we are going to push this address onto the stack again. So now we are setting up a new stack frame, which is the source and destination, to call the function string copy. Then we will call the function string copy. String copy will copy whatever P points to our buffer, right? And this is where the vulnerability, the vulnerability is. If your input is 6 bytes, it's okay. When you input 6 bytes, it will actually write 6 bytes and also a 0 here. So it doesn't really change the J. But if you write more than 6 bytes, 7 bytes, 1 byte will go in here, right? So J will be changed. If you write more, so in this class, today's class, we only talk about override this part. So in Wednesday, we will talk about how we override this part, the return, and what we can get. Actually, even if you do not override return, you only overwrite the old EBP, you can still take control of the computer, but we don't cover that in this class. If you're interested in that, you go to my software security class. So after we call that function, what happens is we are going to and turn to ESP, so ESP back to here. Then the rest is just to clean up everything here, and also there is a print flag system call, because here we are going to compare whatever is in this local variable EBP minus C, compare with 0. Okay, because we already changed that. If we overflow this, we change this, so this compare will result they are not equal, which will print flag. Otherwise, it will print I pity the fool. So that's how it works at the 64-bit version. 32-bit version. 64-bit version should be similar. Let's take a look. 64-bit version, we look at overflow local 64. Buffer. So 64-bit version, I think you probably need 7 bytes. Oh, 7 bytes also works. Okay. If you look at the disassembly, then you will understand why it works. C code the same, but the binary code level, you can say here we have the string copy. Here we call the string copy, and we only need to look for the destination it is copying to, which is at the in the register RDI, and you can say RDI get its value from RAX. RAX get the value from RBP minus A. So in this case, buffer is actually at RBP minus A, which is RBP minus 10. However, the global variable, the local variable J is at RBP minus 4. You can say RBP minus 4. So their distance is still 6 bytes. That's why if you input 7 bytes, you overwrite into that local variable, and you get the flag. Okay, so let's take a little bit more complicated example. This one, the same vowel here, almost the same vowel. The I here, the I here is not 0 anymore. It's the number of command line arguments, in this case 2. Then the same string copy vulnerable. However, you have to input, you have to make J to this exact number to trigger the print flag. Otherwise, it doesn't, right? So the idea is the same. Let's say we run this. Overflow local 2. If we disassemble this program, we get the instructions. You can say the vowel here, that's the string copy. And we are copying whatever you input to EBP minus 12 here. And we are copying from the source is EBP plus C, which is the second argument of this function. And the local variable J is at address EBP minus C. So you can say 18, this is 18, this is 12. So the buffer is exactly 6 bytes, right? So which means if we run this program, if we only give 6 bytes, it will not overwrite that local variable J. So it will show IP the full. If we give it a bit more, it will overwrite into J. However, J will not equal to this value. We just type a random value there. So it will still show us IPT the full. So what you really do is you run this program, you give the exact address, the exact value the program asks for. Let me check the syntax here. We use this print. So that's a value. Yeah. So the syntax here is the $sign means we will execute this command first. Then the output of this command will feed in to this program as a command line argument. So here, what we print out is we will print out the hex value 1, 2, 3, 4, 5, 6, right? So let's say we can do this. It will print out that. Those are not readable. It's not showing here because that's not printable ASCII. But if we do let's do a hex dump. It's not printing anything? Did I? It's not printing anything. Hold on. I think my syntax is wrong here. I need another quote, I guess. Yeah, there I need a double quote. Otherwise, it's not executing. So this one will be the Python. This one will be the Python command here. Should we use Python 2? Because because we installed Python 3 here. So Python 3 syntax changed. Here we have to use Python 2. So you can say let's do, how do I do byte? Just B? No, B is character, I guess. Character hex. Anyone use hex down? 1 byte should see. So, but this is not hex. BCX. I'm trying. Okay, anyway. I want to show the hex value of each byte. So X will be 2 bytes actually. So, anyway. Even without this part, so basically we're printing out those 4 bytes, but some bytes are not printable ASCII. That's why we're not saying it here. Then, so okay, go back to this variability, this program. What do you guys think we should input here to get the flag? Anyone who didn't take my software security class? Okay. Okay. Did you take my class? Okay, cool. So we, like you said, we send 6 bytes of garbage there, right? Because we don't really care what we fill there. So let's just say the garbage is A, then we do 6 bytes. Then after that, we print those 4 bytes. Let's say is this correct? Is this what you want? Should be what? Okay, so first of all, syntax error here. Sorry about that. Okay. Doesn't work. The opposite because of the undiness, right? Okay. So then we do 78, 56, 34, 12. That's how you get the flag, right? Okay, so that's 2 simple examples that we only overflow a local variable here. Wednesday, we talk about how do we overflow the return address. That is originally the Morris, Worm, and a lot of other buffer overflow works is to take over this return address. Because the return address technically is a code pointer. It points to a code. If you can control this one, you can ask the CPU to execute whatever code you want it to execute. So then you basically take fully control of the CPU. Okay, any questions? Okay, if no questions, then see you guys Wednesday. We just posted homework 3. You have 9 days to finish homework 3.